Hello, this is section 4.7 for Calc Survey, and today we'll be talking about logistic growth. And we're starting off with an example about the population of the United States from 1790 to 1860, and it grows exponentially, and here's our function. However, from 1860 to 1940, what do you notice happened? So this is the data from 1790 to roughly 1860 here. That's the data. But then if we expand it, you'll notice, our exponential function that's right here is not fitting our data very well anymore. And if you think about it, we don't want the United States to keep growing exponentially. We need it to, what we say, level off. So instead, we have a better equation here that fits the data better. And so you notice it starts off growing exponentially at first, but then you'll notice the concavity starts to change from concave up to concave down. And that's going to give us a better equation, a better fit for that data. Now, as it starts to level off, we call that the carrying capacity. So you'll start to see that it starts to level off, and where that horizontal line is what we call the carrying capacity. So this is the equation for this curve right here that fit the data better, because you can see the data start to level off. And that's called a logistic function. So the model predicts for the initial and maximum population. So the initial we plugged in 0, got 3.9. And then as we approach infinity, so as these t-values get bigger and bigger and bigger, you can see that we actually level off at 187 million. Okay, so the first graph below includes all the years from 1790 to 2000. Do you believe the model is wrong or the model's parameters are wrong? Look at the second graph with an exponential and logistic model to decide. So this is our exponential model that you can definitely tell is not a good fit. Whereas if you go with a logistic function, that's going to give us a better idea of what's really going to happen. So the model's parameters need to be adjusted to make a new carrying capacity of 450. So this was the existing model that we had up here that had us leveling off at 187 million. And that's not, you can see that's not a good fit for our data. So we had to adjust the parameters to get a better new adjusted carrying capacity of now 450. Okay. All right, so that's just an application of the logistic function, but here's how it works and what the variables are. So this is a logistic function, L being in the numerator, that's your carrying capacity. Notice when we went off to infinity, we ended up getting 187 was what we're going to level off at, and that's the numerator. The point of diminishing returns is the inflection point where P is growing the fastest and occurs at P equals L over 2. So if you take the numerator, divide it by 2, that gives us the P value. Now be careful. A lot of times they'll ask this question, but they'll say, when is it growing the fastest? So you'll then have to set your equation equal to that value and then work backwards and solve for t. So that'll take a little algebra skills. All right, and then lastly, the logistic functions approximately exponential for small values of t with growth rate of k. So that k value, that's that exponential at the very beginning, but then it starts to level off, and that's why we have the largest logistic function. And then C represents a constant. Sometimes you'll have to solve for C in order to get your logistic function set up. Okay. All right. Sorry, this kind of didn't copy very well. So a rumor spreads among a group of 400 people. The number of people who have heard the rumor at a given time since the rumor started to spread can be approximated by the function. So if you think about it, yeah, a rumor eventually is going to level off. People stop caring, or the group of people, everybody now knows. So perfect fit for a logistic function. All right, find n of 0 and interpret it. So if you plug 0 in for t, you end up getting 1. Oh, that makes sense. It takes one person to start a rumor. How many people will have heard the rumor after 2 hours, after 10 hours? And t is in terms of hours. So go ahead and plug 2 and 10 in. So you end up with 2 people know after 2 hours, 10 people know after 48 hours. I obviously need to update my equation because with technology, it's a little different now. People know a lot faster. Okay, now here's a rough sketch. So notice I'm having it start at 1. the value of 1, and then I'm going to level off at 400. 400 is your carrying capacity. That's the limit of people who are going to find out. Approximately how long will it take 3/4 of the people to have heard the rumor? So I multiplied 400 by 3/4, set that equal. And then here's where you're going to have to use some algebra skills. So I cross multiplied, and then you've just got to get that t by itself. So divide by 300, subtract 1, divide by 399, so you can natural log both sides, then divide by negative 0.4, and there's reading your time. So you will have to be able to solve that algebraically. Okay, and then approximately when is the rumor spreading the fastest? So that's that L over 2. That's going to be this inflection point when you change concavity. That's when it's spreading the fastest. And you can see that. That's when the slope of the tangent line is the steepest. So solve your L over 2. You get 200. Set that equal to your logistic equation here. And then again, you just repeat this process. So cross multiply, subtract by 1, divide by 3, and so forth. And I think if you've done enough of these, as you do your homework, you'll get good and you'll be able to do all of this in your calculator without having to write any steps down. Okay. All right, but that's the general idea of a logistic function. So it's kind of nice. And hopefully it'll fit with our COVID situation we currently find ourselves in, and we're eventually going to level off. So it will definitely. All right, now this last example here. So the rate of sales of an automobile anti-theft device are given in the following table. Okay. Now realize that's sales per month, so that's going to be a rate. So that's actually your derivative you're looking at right there. So when is the point of diminishing returns reached? When is it growing the fastest? Okay, when is that sales per month the greatest? So that's why it's at the 4th month. Then in part B, what are the total sales at this point? Okay, so remember, we were looking at the rates of change. So you'll notice underneath, if you've been operating for a month, and those are your sales for that month. But after 2 months, you're going to want to build on that. So you did 140 the first month, add that to 520 that you produced during the second month. And then you can kind of see how you take the 660, add the 680. That's where we're getting these numbers from. So what are the total sales at that point? So at the 4th month, those are your total sales. And then assuming a logistic growth sales, estimate the total potential sales of the product. So, okay, so if it's a logistic growth, what are the potential sales? What is that carrying capacity? So use your P equals L over 2, and you work backwards. So knowing those were your total sales, then you can work backwards and solve for that L value. So just a fun way to apply the logistic curve. Okay, so make sure you do your homework. You'll have to know, especially this L over 2. P equals L over 2, you definitely need to know that. Don't forget that little negative sign. But other than that, it's a pretty straightforward concept. You just have to do your homework like normal. Okay, let me know if you have any questions.